All right, so the main thing right now is to make sure that you have turned in or finished your second try for the exam, right, before the deadline tonight. And once that's done, then I can open up the scores and let everybody know how you've done. All right? Hopefully on this second one, everybody's getting all the points. Okay, let's quiet down, please. And once you're done with that, there's no homework or quiz or anything over the weekend, right? And you can take a break from organic chemistry for a day or two, if you can handle that. All right. So, yesterday, God, it seems like it's such a long week this week. Those 2 days. Yeah, it was so long. Oh, dang. I feel so bad for you guys. All right, so yesterday we started into Chapter 7. After we spent a little bit of time just kind of doing a quick review of the material that was on that video that I posted for you guys. So we looked at that alkylation reaction and we applied it to some synthesis examples. So those kind of problems will definitely be building on as we go forward and will be part of our exams and everything. So we finished off by just doing kind of an intro to resonance. And we'd seen resonance one time before, at least, when we were talking about acid-base chemistry, right? But we're going to go into it in more detail, look at a lot more examples today, and also go to the point where we can draw out different resonance forms or structures or resonance contributors, like the book calls them. Let's turn this. And then be able to look at various resonance structures and decide which ones may be more stable than others and rank them in their stabilities and things like that. All right, once we've gotten some practice drawing and figuring out resonance structures, then we're going to apply resonance to reactions that we've learned before already. Okay? So any questions about where we're at? What we have to do? All right, so let's do a clicker for today. Start now. We can look at this again and we can see that this again has a plus next to a pi bond going this direction, right? We could do it back the other direction, but that just goes back to where we were, right? But we can do it again. This pi bond, I didn't want to do that. That's why I never use that thing, because I always forget to turn it off. Electrons goes toward the plus again. We draw a new resonance contributor. It has the plus over on the far side of the ring now, away from the CH2 group. We can do this again. Plus over here. In fact, we can do it one more time. We can move it back out onto the CH2 group. Plus here, here, and here. So is that the same structure that we started with? No, it's different. Yeah, the pi bonds have all shifted. So in fact, we could move the electrons around. If we move these around, if we shift them around the the ring like this, we could go back to our starting point, right? So if we wanted to look at the true structure here, we could see that the plus would be spread out between the CH2 group and, oops, well, it's not working, and this carbon, and this carbon, and this carbon. It would be spread out over 4 different positions, all right? Every other position around the ring, exactly. Okay? All right, let's look at the next one. So the next one doesn't even have any charges. And so it doesn't fit exactly into the 3 scenarios that we had, but we could say instead of non-bonding electrons, it has pi electrons next to another pi bond, right? So we can say move, we can do this in 2 ways. I'm going to move them here and up onto the oxygen. Okay, so we're going to move them in one direction. I'll draw these in red. So if we follow those arrows, we'd have this here, minus up here. What else would I have to draw? A plus, where would the plus go? It would be over here, right? Okay, so we're separating charge. We could do it the other way as well. So let me just do it the reverse way. I'm going to take this pair and move them down here, and this pair over here. And then I'm going to draw that in green down here. Right, so this would have a non-bonding pair over here. It would have 2 non-bonding pairs here. Now where would our charges be? What would be on the oxygen? A plus, right? Or a minus over here. So which of these 2 would be better? The top one, right? Because we've got oxygen. We know in this is going to be polar. Electrons are going to be pulled toward the oxygen because the oxygen is more electronegative. So this one is going to be really not very good, right? This is going to be much less stable. So it's not going to really contribute to the character of that molecule, all right? So we can draw a few more here, though. We could, let's see what else. We could just move this one this way, right? We've got a plus charge next to a pi bond. That would allow us to go to here, right? So in that case, all we've really done, if we go from the starting point, is just show the polarity of that ketone. And then there should actually be just, what else do I want to do here? Minus, plus, minus. Well, I could also, if I just took this pair of electrons up here and moved them down and moved them over to this carbon, right? We really have non-bonding electrons next to this pi bond. I could come up with one more. We're just going to draw all of these. So this would go like this. And really, in this case, all we've done is really separate charge on this other double bond, like this. All right. So, if we look at those 4 resonance contributors, which one would be more stable? First one, right? Because the first one has complete octets, no separation of charge, right? So this one over here would be the most stable out of all of them, right? The neutral one. All right, and then all the rest of those atoms are missing an octet for one atom, right? So which of those other 3 do you think would be the next most stable? Yeah, some of these are kind of hard to say. Maybe, right? Oxygen's going to be best, right? The second and third ones should be next most stable, right? So which one of those do you think would be more stable? Third one, probably, right? Because the minus is on oxygen, which is good. Plus is on a more stable atom. But we could debate different things here. So we'd maybe say this third, and then this would be fourth down here because the minus is on carbon rather than oxygen. So what does this tell us, right? So what it can tell us, first one is the most stable, right? That's going to be the one we're going to see the most. However, when we draw these out, what we could see is that we essentially have a polar system, and we have kind of like alternating charges, right? So the oxygen we know is going to have a delta minus. Carbon next to it, the carbonyl carbon, is delta plus, right? We know in that bond it's going to be polar, so it's going to spread the charge. The next one is delta minus. The next one is delta plus, right? So the plus and the minuses are kind of alternating as we go down this system right here. All right, so if we look way ahead in this class, let's imagine that we're going to react this system here with a nucleophile. Okay, so a nucleophile, right, is looking for, what is a nucleophile looking for? A nucleus, right? It loves the nucleus. Right, so it's going to go toward the plus. So where would the nucleophile react with this system right here? Right? It could react at the two positions where there's plus, right? Minus and plus come together. So this could potentially react at this position or at this position. Okay? So just by this resonance, we can start to predict reactivities already. Okay? All right, so let's look at the last one. What can we do to show some resonance for this last structure? All right, we've got some non-bonding electrons next to a pi bond, so let's try this first. Let's move these electrons down and move these electrons over here. Right, so that's one thing we could do. And if we did that, we get a double bond between the carbon and the nitrogen, and another double bond over here. We had one non-bonding pair on the nitrogen already. We just moved another pair over there. So where's our minus charge going to be? On the nitrogen, right? The plus remains on the other nitrogen. Okay, so we could do some other things as well. I'm going to do this. I'm going to just take these pi electrons and move them over onto this nitrogen. I'm going to move them toward the plus. So if I do that, I still have the non-bonding electrons and a minus on the carbon, but I've put some non-bonding electrons on the nitrogen, and we have one pair of non-bonding electrons down there. So now where does our plus go? On the far right position, right? So, can we do any more resonance from here? It doesn't just go back to one of the other ones we have? Do we have anything that fits into one of those kind of generics A or B scenarios? A, right? Because we have non-bonding electrons on the carbon next to another pi bond. So let's just move these down this way and move these over here. We can get one more structure. There's that. Now it only has a single bond to this nitrogen with two non-bonding pairs over there. All right, so do we have any charges on this one? Positive on the carbon.
Carbon's neutral. Negative on the nitrogen.
Plus on the far nitrogen. It's got to be net neutral, right? So if there's going to be a plus or a minus, there has to be both. Any charges? No, there's no charges on this one. Sound like Kenny. Woohoo. All right, so let's look at these four and kill Kenny and decide which of these would be more stable. So what do we look at first? Full octets, right? Which do some of them have full octets for all of the atoms? Yes, which ones? First one does. Is that the only one? The one in the blue as well. So the top two have complete octets for all of the non-hydrogen atoms, of course. All right, so between those two, which one do you think would be more stable? The blue one? Why would the blue one be more stable? Right, it has a minus charge on the more electronegative atom. Right, so we could, based upon our rules, we'd predict that this would be the most stable. Right? This one would be second because it's the other contributor, resonance contributor, that has full octets. All right? And the bottom two, I guess we would say the one on the right, right? Because, well, let's see, both of these structures have an atom that doesn't have enough electrons, right? So the one on the bottom right has only 6 electrons on the nitrogen on the right. What about the one on the left? Same atom, right? Has only 6. But the one on the left has a separation of charge, and the one on the right doesn't. Right? So I would probably rank this as number 3, and this one as number 4. Right? But probably the two structures that are going to contribute the most would be those top two. All right? All right, so let's look at a couple more here. All right, we already did that one. All right, so what scenario do we have, A or B, for the top structure? A, right? We have non-bonding electrons in the nitrogen next to a pi bond. So these electrons can move towards the pi bond, or no, yeah, toward the pi bond, and the electrons there can go over on the other end of the pi bond. So we're going to get a double bond out to the nitrogen. We're going to have non-bonding electrons over here. So we're going to have a plus on the nitrogen, minus on the carbon. All right? Just like before, once we're in the benzene ring, we can keep going too. All right? So now we have non-bonding electrons. These can go to form a pi bond. Push those electrons over to there. the electrons to the far side of the ring, minus. We can keep going. Plus there, minus over here. And then we can do this one more time. These electrons go back onto the nitrogen. Alright, and now we have the double bonds like this, which are just shifted from what we started with. Right? So we could draw our arrows to convert this structure back to the starting one. Right, so this goes back here. All right, so I guess the take home here is we already saw an example where we had a plus charge that was distributed around the benzene ring, right? Benzene rings are also good at stabilizing minus through resonance, right? So these benzene rings can have lots of resonance. All right, let's look at the bottom one. Okay, which of the scenarios is this one going to fit into? Yeah, question.
I just have a general question. Of those two that start and finish the benzene rings, is there one more that's particularly stable?
The first one and the last one?
Yeah.
No. The first and the last one would just be identical in energy. Yeah, because the ring is all symmetrical, right? So it doesn't matter which position.
That's why you like to use this sort of-
Yeah, so sometimes you see it with a circle, right? So those are just equal. So which scenario is this bottom one into? This is A, right? Because we have non-bonding electrons on this nitrogen, and they're next to a pi bond. All right, this oxygen has two non-bonding pairs here, but these electrons can move towards the oxygen. Like this. So which of these two would be more stable?
Right.
Which one?
On the right.
On the right? Why would that one be more stable?
Just because the oxygen is more electronegative.
The oxygen has as a negative, that's true, plus on the, but the one to the left has no charge at all, right? So we haven't done any separation of charge, so this one would really be more stable. Okay, but it turns out that the one on the right does contribute a reasonable amount to the overall structure. Okay, so let me show you how. Okay, so let's start with this this nitrogen, I mean, right here. So what would we predict the hybridization to be for that nitrogen? sp3, right? Because it has 3 bonds and it has that non-bonding pair of electrons. So what would the geometry be expected to be? Tetrahedral, right? Okay, what about the same nitrogen over here? What should its hybridization be? sp2, which means that it's trigonal planar. All right? But if there's going to be resonance here, then that resonance cannot involve a change in hybridization. Okay? Because resonance only involves the movement and sharing of electrons, not the movement of bonds or bond angles or atoms. The atoms cannot be moving. All right? So if these are going to be in resonance, what does that mean? In order to allow resonance, one of those two atoms has to be a different hybridization in geometry than what we predicted. Okay, which one should be changed?
One on the left.
The one on the left?
Because if it doesn't have a pi bond, or if it doesn't have a p orbital to share those electrons to, then they can't have resonance.
Exactly. So this one on the left, you ever hear that? Because this one on the left, if it's sp3, that means there's no p orbital there, right? It can only have resonance if there's a p orbital. All right? So in this type of bond, this functional group is called an amide. And in fact, what happens is that nitrogen rehybridizes to sp2, all right? And then there can be resonance.
So how does that pair of electrons work?
That pair of electrons is being shared between the nitrogen and the oxygen. Right? So more of the charge is on the oxygen, right? What we would think here anyway is that the oxygen is more polar, so it's going to kind of pull the electrons that direction, right? And the place we can see this is that this type of amide bond is the type of bond that connects amino acids together in proteins, all right? And the nitrogen in these proteins is planar rather than tetrahedral. And that has a big impact on the shape and the geometry and the folding up of peptides into proteins, because they have to fold into their structures. So this one is a little bit different than what we would expect. So the nitrogen has to rehybridize. It has to essentially push the bonding electrons closer to the non-bonding electrons, right? Instead of 109.5 in tetrahedral, they have to be pushed together to 90 degrees, because the p orbital is perpendicular to the sp2 orbitals. But by doing that, it gains resonance, right? So it donates a little energy to rehybridize, gets big payoff when it gets the resonance, all right? All right, so let's just see if we can finish on a couple here. So what do you think the top one? Can there be resonance between the two pi bonds? No, why not? Right, because it cannot, because there's a sp3 hybridized atom in between those two. There's no p orbital there. Okay, so this one has no resonance between those two. Okay, what about the next one? And this would be called isolated double bonds, or isolated pi bonds. No resonance. What about the next one down? Could we have resonance there? Yes, right? Which is just like the bottom one. We already did the bottom one, but we could move these electrons in one direction here. Or the other, right? Because this one is symmetrical. Right? So if we did that, we'd have a plus over here, electrons over there, and a minus over there. All right? This system where the double bonds are next to each other and we can have resonance, these are called conjugated dienes. Conjugated diene, or pi bonds, let's just say that. All right? And even though the resonance contributor on the left would be more stable, the one in the middle also contributes some to the overall character of the molecule. And the way that we would see this is that when we draw this, let me redraw this over here. This center position right here, even though we draw it as a single bond in the most stable one, has a partial double bond character, which means, partial pi bond, that it is more difficult to rotate around this bond. Remember, we can't rotate around pi bonds. And so, in fact, what we have is we really have two different conformations that don't equilibrate super easily, like this and like this. So this is more of a, takes more energy to rotate. This one up here, because the single bond is kind of, well, let's do this one down here. where we have kind of the double bonds facing to the same side. They call this, and I don't even know what this S stands for, but it's called S cis. And this one up here is called S trans. And it's difficult to rotate this between them.